All right, welcome. Have you ever wondered why some things, they bend and other things just snap? Well, it turns out every single material has a kind of hidden story, a unique signature that tells us exactly how it's going to behave under pressure. So let's dive in and decode that story.
It all kicks off with a super simple question, one you've probably experienced yourself. Why is it that you can bend a paperclip back and forth, no problem, but the second you drop a coffee mug, it shatters into a million pieces? They're both solid objects, right? So what gives? Well, the answer, it's all about how they handle force.
Okay, so the first piece of this puzzle is a concept that engineers call loading. And really, it's a super simple idea. Loading is just the act of applying an external force to something. Pushing it, pulling it, twisting it, any of that stuff, that's all a form of loading. And engineers have kind of broken these forces down into 5 main types. You've got compression, that's basically squishing something. Then there's tension, which is pulling it apart. Shear is a little different. It's like sliding one part of the material past another. Torsion is just twisting. And bending, well, that one's pretty self-explanatory.
Okay, so when you apply one of those forces, the material doesn't just take it. Oh no, it fights back. And that internal resistance, that pressure it feels on the inside, that's what we call stress. But here's the really interesting part. It's not just about how much force you're using. It's about how concentrated that force is.
And the formula for it is just beautifully simple. Stress equals the force divided by the area it's applied to. So what does that really mean? It means if you have a smaller area but the same amount of force, you get way higher stress. Just think about the difference between someone pushing you with their whole hand versus just one finger. Same force, right? But a totally different feeling, a totally different amount of stress. So you've got this material, it's under stress. What happens next? Well, it deforms, it changes shape. And the way we measure that change, that deformation, is with something called strain. Strain is really just how much the object stretches or squishes compared to its original size. It's a ratio, kind of like a percentage, which is why it's weird. It actually doesn't have any units.
Yeah, you just calculate it by comparing how much the length changed to what the length was in the first place. Super simple. And that gives us a really precise way to talk about how much something has deformed. So there you have it, our 2 key players. Stress, which is the internal force, and strain, which is the deformation that happens because of that force.
Okay, now we can finally start reading a material story. And the first chapter is all about predictable, well-behaved reactions. It's all governed by this one simple, really elegant rule.
This rule, it's called Hooke's Law, and it was figured out way back in 1660 by Robert Hooke. And what it basically says is that for pretty small stretches and squishes, the amount of deformation is directly proportional to the force you're putting on it. But here's the crucial part. When you let go, when you remove that force, the object springs right back to its original shape, just like a rubber band, and that's what we call elastic behavior.
So, how do we actually measure this springiness? Well, that's where something called Young's modulus comes into play. It's just a number that tells us exactly how stiff a material is. You calculate it by dividing the stress by the strain, but only in that elastic, springy region. So, a high Young's modulus, that means a material is super stiff and really resists being stretched.
And this right here just illustrates the difference perfectly. Take a look at this comparison between aluminum and steel. Steel's Young's modulus is roughly 3 times bigger than aluminum's. So what does that actually mean in the real world? It means you'd have to pull 3 times as hard on a steel rod to stretch it the exact same amount as an identical aluminum one. That is a huge difference in stiffness. But what happens if you just keep pulling? What happens when you push a material past that polite, springy, elastic zone? Well, that's when the story starts to get dramatic. This is where we go beyond elasticity, and we start to find out where a material's breaking point really is.
To get the full story, engineers do something called a tensile test. It's pretty straightforward, actually. They take a little sample of the material, they clamp it into this really powerful machine, and then the machine just pulls it apart at a nice, constant rate. And the whole time, the machine is recording exactly how much force it's using and how much the sample is stretching. Then, it takes all that data and plots it on a graph.
And what does that graph create? This, the stress-strain curve. And let me tell you, this graph is everything. It's the material's unique signature. It's the secret code. It's the entire life story of that material under tension, from the very first gentle pull all the way to the final catastrophic break.
So let's follow the story. It begins right here in the elastic region.
You see that perfectly straight line? That is Hooke's law in action. Stress and strain are perfectly proportional, and as long as we stay on this part of the curve, if we were to let go, the material would snap right back to its original size. No harm, no foul.
But then, we hit the plot twist. It's called the yield point. You can see it right where the line starts to curve. This, my friends, is the point of no return. Once you go past this point, the material is now permanently deformed. We've just entered what's called the plastic region. Even if you let go of the force now, it's never ever going back to its original shape.
Now, as we keep pulling, something interesting happens. The material actually gets a little bit stronger for a while. That's a process called strain hardening. But eventually, we reach the climax of the whole story, the ultimate tensile strength, or UTS for short. That's the very highest point on the curve. It represents the absolute maximum stress the material can possibly handle.
And after that peak, the story enters its final, tragic chapter. The material just can't take any more stress. It starts to get thin in one specific spot. Engineers call this necking, because it looks like a little neck is forming. After that, the amount of force needed to keep stretching it actually drops, until finally, snap. It fractures. The end. So, now that we know how to read one of these curves, we can start comparing the stories of different materials. And this is where we finally get the answer to that question from the beginning.
This table breaks down those different stories perfectly. So you've got your brittle materials, like a ceramic. They can handle a ton of stress, but they have almost zero plastic deformation. They just break suddenly. Then you've got ductile materials, like copper, which have this huge plastic region. That means they stretch and stretch and stretch before they finally fail. And then there are things like polymers, which start deforming really easily, almost from the get-go.
So let's really zero in on that key difference, brittle versus ductile. The coffee mug, that's our brittle material. It's strong, but totally inflexible. And when it hits its limit, poof, it fails suddenly and with absolutely no warning. But the paper clip, made of a ductile metal like steel, is the opposite. It can be stretched, it can be bent into a new shape. That's its plastic deformation. And, crucially, it gives you a warning sign. It stretches and necks down before it finally breaks.
So, for any ductile material, you can really think of its journey as having these three distinct parts. First, there's the reversible, elastic phase, where it just springs back. Then it moves into that permanent plastic deformation phase. And finally, it hits the end of the line, fracture and failure.
And to get a little more specific with that ductile materials story, just remember those three stages you see on the curve. You've got the elastic region, then that strain hardening part where it gets stronger, and finally the necking phase right before it breaks.
So there you have it. You now have the tools to look at a material and decode its secret story, which leads me to one last question for you. If you were an engineer, what kind of story would you want for, say, the steel in a bridge? And what about the material for a car bumper that's supposed to crumple and absorb impact? Think about it. The story you choose makes all the difference in the world.